Hello everyone. Today we are going to study transportation problem. It is an optimization technique used in operations research. Most of the material in this presentation is from Hamde A. Taha's book on operation research and the book of Wine Winston. The content of today's presentation is: given a situation, identify when to use a transportation algorithm. In which conditions we can apply a transportation algorithm. Secondly, we will able to understand the basis of transportation algorithm and see a comparison how it differs and how it similars with the simplex algorithm. Thirdly, we will able to generate the basic solutions, the basic feasible solutions as we did for the case of simplex algorithm. And lastly, we will able to optimize the problem using transportation algorithm. It is again akin to the simplex algorithm where we do different iterations. Recently, Amazon has launched its pantry service across UK. A pantry will include fast-moving consumer goods, and they promise to deliver it within 24 hours at the price of £2.99. The customer will order online from their home and they will get their service within 24 hours. Let's assume for generality that pantry is a single product and is same for every customer. Now, what Amazon is doing here is that they have their warehouses at different locations across UK, and they want to deliver to their customer the pantry within 24 hours. So they will see that which location is nearest to them, and the objective here is to deliver orders from multi-locations to multi-destinations with minimum cost and within stipulated time. Here I would like you to pause for a second and think of the situations where the transportation algorithm can be applied. Think of a scenario where you have one product and you have to deliver it from multi-sources to multi-destinations. Moving toward next section, let's try to see what are the basics of transportation algorithm. First of all, transportation algorithm or transportation problem is a special case of a linear programming problem. In fact, it is a subset of linear programming problem. Secondly, because of its characteristic, the transportation problem can be solved very efficiently with a special algorithm that's called a transportation algorithm. Let's look at the scenario. We have m different sources and n different destinations. Our m sources are producing a single type of product and there is a demand on the destinations. Supply capacity for a source M is represented by AM, and demand from destination N is represented by BN, and the cost to deliver an item from source M to destination N is CMN, and the number of units which we can send from source M to destination N are XMN. Let's try to understand the concept with the help of a car distribution problem. The MG Auto Company has plants in Los Angeles, Detroit, and New Orleans. Its major distribution centers are located in Denver and Miami. The capacities of the three plants during the next quarter are: for the first plant, it's 1,000, then 1,500 and 1,200 cars respectively. The quarterly demands at the two distribution centers are 2,300 and 1,400 cars. The cost of shipping in dollars per car is given in the table. In order to ship one unit from Los Angeles to Denver, it costs $80, and from Los Angeles to Miami, it costs $215. Similarly, the costs are given for Detroit and New Orleans plants to deliver to Denver and Miami. The question is to find the best strategy to send cars from destinations to distribution centers with the minimum possible cost. Let's Xij are the units sent from location I, that are Los Angeles, Detroit or New Orleans, to destination J, that is Denver or Miami. We solve it as a minimization problem. The objective is AT, which is the cost of transferring one unit from Los Angeles to Denver, AT XLV plus 215 XLM, which is the cost for delivering from Los Angeles to Miami, and then is 100 XDV, 108 XDM plus 102 XNV and 68 XNM. The constraints are XLV plus XLM is equal to 1000. First we show the constraints for the supply limit, which is 1000 for the Los Angeles. Then we presented a constraint for the supply limit of Detroit, which is 1500, and the third is the supply limit for New Orleans, which is 1200. And the next two constraints are for the demand. For the Denver, the demand is 2300, and for Miami, it's 1400. Subject to all the variables must be greater than or equal to 0. Now this is in a standard linear programming problem form, where we have objective function, which is a summation of the costs per unit, and we have constraints. One is the constraint at the supplier side, which is the summation of all the suppliers, and the other is the constraint at the destination side, which is the summation of all the demands at the destination, subject to all the variables greater than or equal to 0. This standard linear programming formulation can be converted into a transportation tableau. Since we mentioned that transportation algorithm is to solve a special class of linear programming problems, which are transportation problems. So the easier way is to form a tableau. In the tableau, we can see we have sources S1, S2, S3, and we have destinations M1, M2, M3, M4. And now here we have units from source I are AI, and units from destination B are BI, and the decision variable, which is cost, which is the units Xij, and the cost for sending a unit X from source I to destination J is Cij. And for our car distribution problem, our tableau will be look like as shown. The costs are there in each box on the lower side, on the lower right corner. For example, from Los Angeles to Denver, the cost of sending one unit is $80, and the unit to be sent from Los Angeles to Denver are X11. Similarly, we have for X12 and X21, X22, X31, X32. And now the supply capacity of Los Angeles is 1000 units in the last column. For the Detroit, it's 1500 unit, and for New Orleans, it's 1200 unit. Similarly, the demands at Denver is 2300, and the demand at Miami is 1400. So here we have now formed the initial tableau of the transportation algorithm. And next we will see how to make a basic feasible solution for the transportation algorithm.